And Thursday's all about volcanism. We're going to be melting the earth. And when we melt the earth, we first melt in the mantle. And we melt the mantle, we get basalt. And it's black. Don't you get it? Painted black. It's black. So this is all basalt. So today we will focus largely on painted black basalt lava. Lovely basalt lava. But before we do that, oh, there you are. Let's get out those clickers and see how we did. This is Tuesday. How well you recalled what you had now, what, 4 days ago? Hey, look at that. Look at you. And we never know how this is really going to go. Not yet. Try it again. I know that. One more time. There's a whole lot of you been adding this course very recently, and that's fine. You're welcome here too. We will soon, I hope, have these videos available for you through a YouTube version on Boston, B University, right? So we're working on getting those ready. And we also have a backup video going. You maybe not knew this, but back there is another camera, stationary, that fills the screen with these two screens and the podium, which I'm rarely at except for right now. It's a bit more stagnant. I think the one that our TFs are doing with the handheld camera, bless them, is a bit more helpful. Well, this didn't launch either. Let's re-crash it. Failed to start, I know that. There we go. Woo, woo, woo. You don't scare me. You want to know the truth? Plate Tectonics 2. So that's our 4th lecture. So far you've had 4 lectures. And the videos that we're putting out for you will, at this time, will have also the clicker sessions. Because so many of you are new, you have not had a chance to be here. In general, in the future, I won't always have the clicker sessions. They're really for those that are here. But so many of you have just added the courses. I've not added the clicker sessions out of the videos. And so here we go. What is all of that? Help. Help. Okay, reset slides. So take just a minute, get it out, get it ready. This is 3% of your grade. There are 11 slides here. Oh my gosh. That's right. Response devices, automatic. I would love to get this ready to go before I came in the classroom, but it doesn't like me to do that either, I think. Keep trying to find the right way to do this. All right. a magnetic reversal, the Earth will turn upside down. What do you think? Now, magnetic reversal, let me re-emphasize that. A magnetic reversal is when the poles flip. The poles do this every 200 or so thousand years, sometimes more rapidly. And the North Pole points north and the South Pole points south, and then it reverses itself. South goes north, north goes south. These are called magnetic reversals. And when we look at the magnetic character of the ocean floor, we find this polarity back and forth over time. That's additional symmetry we have about the ridges. So the poles do flip, but does the Earth go upside down? I now open the poles. Great, there's the countdown. Hurry, hurry. 5, 4, 3, 2 seconds. You got it? And you said, wow, I'm not fooling you. 97% said false, and that's the correct answer. Way to go. Most of the Earth's seafloor has been recycled back into the mantle. All right, poles are open. And there's the countdown. Hurry up, hurry up. Get those clickers out. Just 4 more seconds. Doesn't matter what you say. This is a safe haven. And you said, 86% said true, and that's the correct answer. What do we mean? Why do I say that? Because the Earth's seafloor everywhere is very young. The oldest rocks are where? In the continents, okay? The Earth has been here for 4.6 billion years. The oldest rocks are in the continents of 4.0. When we go into the oceans, it's everywhere very young. Less than 220 million. With a symmetrically to the ridges. The ages are distributed symmetrical to the ridges. Youngest at the ridges and also at hot spots, as we'll see today. The greater the distance to an earthquake epicenter, the longer the time period between the primary and secondary waves. Okay, poles are now open. Greater the distance. How far away was that earthquake? Which one comes in first, S or P? P, there you go. And now the countdown is on. 10, 9, 8. Keep it coming, keep it coming. Are you taking pictures? Atta boy, atta girl. Don't call me boy. Okay, 95% said true. And that is the correct answer. This is just like lightning and thunder. P waves move out fast, almost twice as fast. When the earthquake's really close to you, boom, happens all together. Can't tell them apart. But as they get further away, the San Andreas Fault is a boundary between the North American and Pacific plates, the latter presently moving northward toward the Aleutian Trench. There's a very complicated long sentence. Is it true? And now the poles are open. Is it a boundary between the North American and Pacific plates? Is the Pacific plate, the latter one, moving northward? Okay, and now I can do the countdown. You've thought about it. Just a few more of you in. You got 7 more seconds. Here we go. Real exam questions. The midterm is 2 weeks away. I don't want to think about it. Okay, 73% said true, and that is the correct answer. So if you're in that 27%, that's okay. Now you can see it. Most people got it right. You might need to work a little bit more. I think reviewing each lecture before each lecture is really critical. Coming to lecture is really critical. So that you see it for the first time in real. Multiple choice. Here we go. The Appalachian Mountains represent the remnants of a Himalayan-type mountain chain. 3 stages of island arc continental collision were rifted, now on both sides of the Atlantic. One stretched from the Baltic region of northern Europe to West Texas, and all of the above, the Appalachian Mountains, right where you are. Is that all of that true? Okay, I'll open the polls now. give you plenty of time. Is every one of those things true about where I live? Could that be right? And some of you didn't quite get in there, but a whole lot of you said all of the above, and that is the correct answer. All right, some of you were scattering around. Every one of those. So I know you like, some of you liked A, some of you liked B, or number 2, some of you like number 3. That's right, because they're all true. All were true. The Sierra Nevada mountains, mostly of granite, igneous roots of Andean volcanic arc, are the testimony that subduction once existed beneath California, contain remnants of island arcs, and all of the above. Okay, you're firing away. Yeah, I kind of do like all of the above at times, and so that's my slant. And you only hear that because you are in class. Okay, countdown is in. But would I trick you? Yeah. Okay, 3, 2, 1. And you said, woo, 80% with all of the above. And that is the correct answer. That check mark just a little bit off. Oh, goodness, this looks funny in an old font. A continental collision results in a double thickness of continental crust, the formation of unusually high mountains within the interior of a continent, Himalayas. The end of subduction takes a while. A fault suture marked by fault-bounded slabs of serpentinite. What do I call it? Spirit of oceans past. And 5, all of the above. Okay, I'm now opening the polls. You can now fire away. It's being registered. It knows you're here. Welcome. Yeah. Oh, open the polls. There we go. 10 more, 8 more seconds. And you said 89% went with, hey, Dr. A likes all of the above. I kind of like it too. And that check mark is in the wrong place. It is all of the above. I'll tell you, nothing I can do about that. It looked good on my computer. The difference in magnitude between earthquakes with a Richter or moment magnitude, 2 and 5. A magnitude 2 and a magnitude 5 is what? In terms of magnitude, not energy, just magnitude. 3, 30, 100, 1,000, 100,000. Or is that a million? That's a million. It's a funny font. So, what do you think? The difference between a 2 and a 5. The difference in magnitude. It is a power scale. Polls are open. You're firing away. There's the countdown. Hurry, hurry, hurry. A 2 and a 5. 3, 30, 100, 1,000, or a million. You work together. She's praying. Okay, 71% said 1,000, and the check mark looks good now. So there you have it. Between a 2 and a 4 is how much? That's okay. Go with your impulse. All right, there we go. There you are. Look at all those movies. Woo, woo, woo. It's all about technology. I had more trouble. I'm all over YouTube looking for new things to show you and insert into the PowerPoints. And you'll be doing that too when you create your PowerPoint, if that's the way you go. But now it seems the PowerPoints need you to click one additional little box. Save this link, or it doesn't work. So remember that. And the movie file has to be with it. So I said paint it black. You melt the mantle. Rolling Stones were saying paint it black. You melt the mantle. The mantle is made out of peridotite, named for the gem mineral peridot. See the green? That's what mantle rock looks like. It's peridotite, peridot, lots of olivine. That's what the mantle looks like. And you melt it, and where it melts is where it's got some water and or carbon dioxide in it, because that lowers the melting temperature. If you have dry peridotite, it's going to take really high temperatures to melt. But a little bit of dissolved water and CO2, life. Where did air come from? Where did air come from? What did we say? Where did air come from? Whew. Oh no, I'm in the wrong place. Sorry. Where did air come from? From volcanoes. All right. Early Earth had no air, and the Earth began to heat on the inside, began to melt on the inside. I'm melting. But where it melted was where there was carbon dioxide and water, and so the early magmas were naturally rich in volatiles, dissolved and held by pressure. Open a champagne bottle, a soda bottle, a beer can, and in that fluid you don't see any bubbles until you pop it open, release the pressures, and out of there come all the bubbles. I should get a beer can up here right now, open it up and dump it into a glass and let all that froth come out of nowhere. All right? And so lava, magma, when you melt the earth, that magma is rich in dissolved gases held. You don't see them held by the pressure of being deep underground. But when they rise because they expand when they form. Magma, melt, liquid is compressible. Under pressure, it gets compressed. It gets more dense. Deep inside the earth, liquids sink. That made our core. But the outer half of the core, the pressures are less. And liquid expands. And so magma rises where it melts. I'm melting. The magma rises, and it's full of volatiles. But what makes it rise is not the volatile. It's the low density, because it expands. And it's bringing up dissolved gases, and here they come. You look at lava, it's full of holes. Look at all these holes. All right? As this rock was cooling and congealing and bubbling, out came the gases that you now breathe, making air. Look at that. Full of lava. Look at that. Frozen, petrified, fossilized. Breathing out as we speak. So our earth is alive. It's physically alive and biologically alive. And if it didn't have earthquakes and volcanoes, you wouldn't be here. All right? Early earth. Look at that. So the earth's mantle melts peridotite, made out of olivine and pyroxene. These are green minerals. And when it melts, it makes the crust of the earth. And out of that crust bubbles out the first gases even today. So our earth is alive. It breathes out through its volcanoes, and it breathes out through us. We're breathing out, and it breathes in through its life as well, photosynthesis, and it breathes in through its oceans. So the earth is an amazing planet. Our early atmosphere was what volcanoes were outgassing. Mostly carbon dioxide and water and sulfur. And the clouds were like Venus today, thick. All right? Really thick. But then our earth breathed in. Our earth breathes out. And Venus is still breathing out. Mars has quit breathing. But the earth, doing it just right, Goldilocks example, breathe back in that atmosphere. Breathe in through its oceans. And breathe in through its life. Photosynthesis. Go outside and look at this building. It's 2 blocks long. It's 5-6 stories in places high. And it's in the church in between. And it's all made out of limestone. Don't you see? It's all made out of limestone. The earth breathed in and made corals and ammonites and trilobites. It's a fossil hash, this building that we reside in right now. I don't know how old it is. I don't know where they got this great rock. But there it is, really fine. And it's marbles and limestone all over the earth. Cut up in places, sometimes they make buildings, and otherwise they're in the mountains. The earth breathed in through its oceans and made rock. Later that rock uplifted out of the ocean through plate tectonics, so we can go and climb on it or make a building out of it. So volcanic hazards is our topic today. Here's a beautiful lava rock. We'll learn about volcano, lava, very, very viscous, blocky lava. We'll learn about pahoehoe lava, flowing, ropey, pahoehoe. These are Hawaiian terms. And when the lava goes out, it blows up in places. This is a volcanic bomb. You can see that it's aerodynamically shaped. It came crashing back down to our planet. This is what we call lava toe. You'll see this on the movie in just a moment. I have walked right up to basalt lava, stuck a stick in it. Come to my office, I'll show you. Stuck a stick in it and pulled out a plug of lava. I washed it, you'll see it on the film, turned into a rock, a baby rock, just born. And then I went back. Someone said, step on it, Lawford. I thought, oh, what a great idea. And I went back and pushed it in, got another plug on it, and I stepped on it. And so I'm now fossilized. I've got a footprint of my own boot in lava. I don't say you should do that. It's really quite dangerous. Don't do things I do. But hiking around lava flows, you can actually get surrounded and be on an island with nowhere to go. And if you do go in, I actually went in with some of my graduate students who've been studying there for a couple of years and really knew the country well, and so we had good care. You certainly would never want to go in there alone. Volcanoes are actually quite dangerous, as you're going to see. The basalt lavas they're more safe. They're the only ones I would walk up to. Basalt lava is what the ocean crust is made out of. It also pours out on land in places. But when ocean crust melts, which is what happens in subduction zones, you make the second and third kinds of volcanic rock we call andesite and rhyolite. And those will be the subject of Thursday. Subduction zone volcanism, andesite, named for the Andes, and rhyolite. These are thick, viscous lavas and the most dangerous lavas on Earth. They are the most explosive volcanoes. This is what happens in subduction zones. That's for Thursday. When these volcanoes will erupt, when that lava comes out, I'm going the other way. This is what Yellowstone is all about, for example. This is what the Aleutians, this is what Seattle and Portland, Cascadia subduction zone, all right, Mount Etna in the Mediterranean, very dangerous volcanoes. You don't walk up to them, you fly out of there as fast as you can. So let's go on a road show and look at some of this. All right, volcanic hazards, I'm melting. And I don't think I stuck the thing in, I did not. Here we go. All right, whoa. So as I was saying, it's a part of our planet being alive. The Earth breathes out through its volcanoes and in through its oceans and plants. This is how our atmosphere is made, our crust is made. All comes from the mantle. All comes from the mantle. So if the mantle weren't melting, we would not be here. Magnetism on our planet occurs at plate boundaries and at hot spots. Let's just look at the 7 different places that it occurs. Here is a divergent plate boundary in the ocean, so mid-ocean ridges. Most of these underwater. That's where most of the world's volcanoes are, underwater. All right? And divergent. So this is divergent. Number 2 is divergent. That's a continental rift. Let's go to Kenya. Get in here. Let's go to the Congo. Number 3, subduction zones. This is a Japan-type subduction zone where I'm subducting ocean crust beneath ocean crust. Far more dangerous. Now we're melting basaltic ocean crust. So ocean ridges make basalt. The ocean crust is made out of basalt. But where we subduct it, underneath ocean crust or underneath a continent, that's number 4. Then we're starting to melt basalt. And when you melt basalt, you get andesite. And if you melt andesite, you get rhyolite. Andesite and rhyolite, as I said, far more thick, far more gas. What makes a stick of dynamite blow up? Or a firecracker? The gas of ignition of the fuse cannot get out. It's wrapped in paper, can't get out. And so the gas, there's so much gas in andesite and rhyolite, as we'll see on Thursday, it can't get in. These volcanoes build up a huge amount, go up 15,000 feet high volcanic mountain, and then they blow up, Mount St. Helens style. All right, so 1 divergent, 2 divergent, 3 and 4 subduction zone. Number 5 is a back arc sea behind an island arc, happens there as well. Number 6 is a hot spot out in the ocean, and number 7 is a hot spot on land. Okay, so here's Hawaii, and here is Yellowstone, for example. So let's go on the ring of fire all the way around the Pacific, other parts of the world too. Here is the Mediterranean. It's closing Indonesia. All right, so where we have magnetism on planet is where the Earth is melting. I'm melting. Advancing. It's a magma. I want you to go home tonight. Go to your dormitories. Go right into your showers. Find somebody's shampoo that's clear. Okay, it can be colored, but I want it clear. And take that, go into the shower and take that shampoo and turn it upside down and watch the bubble rise. I don't care if it's yellow, green, or clear. Watch the bubble rise. And in the shower, watch that bubble rise all the way to the top, then turn it back over again. And watch it go back up. And I want you to say one word. Magma. Magma. Yeah, magma. Say it. Magma. Magma is low density melt because it expands. That's why it rises. It's got low density. I'm rising. It's full of crystals, of minerals like olivine and pyroxene and